So this is the free response question from Monday. And before looking at the rubric, I just want to talk through, I guess, what goes through my head as I read a question like this. And uh, whenever you read through a problem, you should kind of search your memory and think about the types of concepts we've covered this year and what might be applicable, because we have covered the content. It's there in your brain somewhere, and so you have to bring it to the forefront of your mind before jumping into a problem. So try to come up with a plan, or at least think of concepts that are connected to the material here and the things that you have actually learned about. So we have a sample of pure gaseous hydrocarbon. A hydrocarbon is something simply that has hydrogen and carbon in it with the general formula CXHY. Okay, so carbon and hydrogen. So it's gaseous. We don't know its chemical formula other than that it has carbon and hydrogen. We introduce it into an evacuated, that means it's empty, no gas at all. Rigid, which means the volume is fixed. 1 liter container. Okay, the pressure of the gas is 0.2 atmospheres. Okay, so we know the volume of the gas sample, we know its pressure, and we know its temperature. And probably one of the most important tools in your tool belt as a chemist is the ideal gas law. We can solve for the number of moles. So that's something that we could do, and we'll see the rubric in just a moment. But if we know everything else in here, the pressure, the volume, the temperature, and the universal gas constant, we can solve for the number of moles in. Okay, so we've got this hydrocarbon in there. We introduce some oxygen into the same vessel. Is the volume going to change? No, the volume is fixed. It's a rigid container. Okay. So after the addition of oxygen, the total pressure is up to 1.4 atmospheres. Same temperature, higher pressure. Okay, we're going to use Dalton's law of partial pressures here. Key term is partial pressure. Okay, the whole idea behind Dalton's law of partial pressures is that pressures add up. So if you know the total pressure, or if you're trying to figure out the total pressure, whatever, it's the sum of the pressures of the individual components. Okay, and it doesn't matter how many components are there. It could have 26 components, but you add up all of those partial pressures. Also related is the idea that the components are independent of each other. According to kinetic molecular theory, gas particles are much smaller than the volume of the container in general. And so if you've got like a green gas and a blue gas, both of these gases have the full volume of the container to move around in. So you can ignore the space that the other gas is actually taking up. It's negligible. Okay, so if you want to find the partial pressure of oxygen, and here's the total pressure, and we already know the partial pressure of that hydrocarbon, we could subtract that out. Okay, so that would be the approach for the partial pressure of the oxygen. We can subtract out the partial pressure of the hydrocarbon and see what's left over. That's the idea. Okay, the mixture of the hydrocarbon and oxygen is sparked so that a combustion reaction occurs, and it produces carbon dioxide and water. Okay, so in a combustion reaction, normally that's going to go to completion. That doesn't mean you have a stoichiometric amount of your reactants, but something is going to run out. The partial pressure of these gases, blah, 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 there is oxygen remaining in the container. Okay, so if there's oxygen in the container after the reaction, we know that the hydrocarbon is the limiting reactant. The hydrocarbon here, whatever its formula is the limiting reactant, okay? And so we can use the partial pressures to calculate the partial pressure of oxygen, calculate the partial pressure of the oxygen that is consumed in the combustion, okay? So there are ways to kind of work through this what we have here, given that we have the partial pressures of our products, okay? And so those partial pressures are directly proportional to the numbers of moles. You can already see that there's more moles of H2O than CO2, and that's because its pressure is higher, okay? So higher pressure, higher number of moles, okay? That's Avogadro's law. And so and then furthermore, if it's a 6-to-8 ratio here, that's 3/4. There's a 3-to-4 ratio of the pressures. And so therefore a 3-to-4 ratio of moles. Okay, and so those are going to be perhaps the coefficients in the balanced equation. Every time we form 3 moles of carbon dioxide, we're going to form 4 moles of water. Okay, so those might be the coefficients there. On the basis of your answers above, write the balanced chemical equation. Those ratios have something to do with the coefficients. Okay, calculate the mass of the hydrocarbon. Once you have a balanced equation, you can use that information to do some stoichiometry. There might be other ways to do it here, although I don't see, if we know the partial pressure of oxygen, there's different ways we can figure out how much oxygen is consumed. We'll have to do some stoichiometry for letter E. And as the vessel cools to room temperature, droplets of liquid water form in the inside walls of the container. Predict whether the pH of the water in the vessel is less than 7, equal to 7, or greater than 7. The question is anything in this container going to dissolve into that water that forms, okay? Because that water is a product. Is there something else in that container which could affect the pH? So let's go ahead and have a look at the rubric here. Okay, so for the rubric for part A, we're going to use the ideal gas law. Remember, degrees Celsius is not the right unit for the ideal gas law. You got to put that into Kelvin. So add 273, it's 400 Kelvin. Remember to use the appropriate units and value for the universal gas constant so that things divide out. And you have about 6.09 times 10 to the negative 3 moles. Okay, so that's the number of moles of hydrocarbon. That's going to be important for later on determining the mass of the hydrocarbon that's consumed. Okay, oxygen's introduced in the same vessel. The total pressure goes up. So that extra pressure is due to the oxygen. So you subtract out the original pressure, the 0.2 atmospheres, and you have that extra pressure added in there. So to kind of summarize what's happening here, the total pressure is the sum of the pressure of the hydrocarbon, I'll just abbreviate that HC for hydrocarbon, and the pressure of the oxygen. And we know what the total pressure is. Total pressure is 1.40 atm, and the hydrocarbon pressure is 0.2 atmospheres. And so the oxygen is the difference, 1.2 atmospheres. Okay, so use the partial pressures to calculate the partial pressure of oxygen consumed in the combustion. All right, so use the partial pressures of CO2 and H2O. Okay, something important to recognize here is we know the pressures of the individual components and their temperatures and their volumes. So we can figure out the number of moles of carbon dioxide and water. And notice something really important about these chemical formulas. They both have oxygen in them. Okay, if we can figure out the total number of moles of oxygen atoms that end up in those products, we can determine how much oxygen reacted away, because this oxygen in the carbon dioxide and that oxygen in the water came from the diatomic oxygen in the first place. Okay, so you've got this reaction between the hydrocarbon and oxygen, and that oxygen that gets used up, you know, it's not the limiting reactant, but whatever gets used up does end up in the carbon dioxide and in the water. This oxygen here and here came from here. It didn't come from the hydrocarbon. Okay, so we've determined that the number of let's see, based off of PV equals nRT, this is the way that I'm thinking through it. The number of moles of H2O, we've got 0.0122 moles of, 0.0244 moles of water, and every time we form 2 water molecules, we would need to use up 1 oxygen molecule. That gives us the same number of oxygen atoms. So in other words, if we wanted to form this much water, which we do form, we would need to use this much diatomic oxygen. We would need to use this much diatomic oxygen for the similar calculation for carbon dioxide. We've formed this number of moles of carbon dioxide, and that oxygen in the carbon dioxide came from the diatomic oxygen. So this is not necessarily from a balanced chemical equation. This is just from the chemical formulas that they're using. Okay, so these are the numbers of moles of oxygen that are required to get the amounts of carbon dioxide and water that have actually formed. And so we add up all of those moles of oxygen, and so that's the total number of moles. Plug that back into the ideal gas law to find that partial pressure of oxygen that is consumed. Okay, and so that leaves behind a little bit of oxygen. Remember, its original partial pressure was 1.2 atmospheres, and here we've used up 1 atmosphere of oxygen. Okay, so there is 0.2 atmospheres of oxygen left over after all of that. Okay, so the partial pressures occur in the same proportions as the numbers of moles. Absolutely right. Okay, so it seems to be the case that there's that 3 to 4 ratio that I mentioned earlier. They have put the number of atmospheres of oxygen that was used up. We used up all of the hydrocarbon, and we produced these numbers of atmospheres of the products. So just straight from those partial pressures that are involved in the reaction, what's produced on the product side and what's consumed on the reactant side, you can find the numbers of moles there. And there are other ways to go about it, but that's just straight from the partial pressures. So the idea here is, once you have this balanced chemical equation, you can infer what the formula of the hydrocarbon is, because it has to have a coefficient of 1 out in front of it based off of these pressures here. Okay, so 1/5 of the coefficient in front of the oxygen right here. Okay, and so if it has a coefficient of 1/5 of the coefficient of oxygen, and then you're balancing up the chemical equation here, you would have to have 3 carbons for the 3 carbons over here and 8 hydrogens for the 8 hydrogens over here. So that gives rise to this formula. Once you have that formula, the molar mass is straightforward because you know the formula. 3 carbons, so 3 times 12.01, plus 8 hydrogens, 8 times 1.01. That brings you up to 44.1 grams per mole for C3H8. And so multiplying the molar mass and the number of moles gives you 0.269 grams. Part F, as the vessel cools down to room temperature, carbon dioxide is present, and carbon dioxide is soluble in water. When carbon dioxide dissolves in water, and this is important, this is something that you should remember, it reacts with water, and it's actually a kind of an equilibrium situation because it doesn't go to completion, but when it dissolves into water, some of it reacts with the water and it turns into carbonic acid. Okay, so this gas, that liquid, gives you a bit of aqueous carbonic acid. Okay, and so this is an acid that forms. It's a weak acid, but it is an acid, so it generates H+. And that H+ is going to lower the pH below 7. Okay, so we're going to get a pH below 7 because we effectively have an acidic solution here. Okay, let's move on to the next FRQ, and I'll talk you through some of the important points. Okay, so we have this decomposition reaction basically where um, one of the hydrogens jumps over here onto the nitrogen, and then that part of the molecule pops away, and then a double bond forms. Okay, so we place some of that original reactant in an insulated container. Okay, that's important for thermodynamics. If you're going to measure enthalpy or something like that, it should be insulated, closed system as best as you can. Decomposes into ethene, that's this stuff, and ammonia. Okay, so here's the entropy values. Entropy is a measure of disorder, and just looking up here, the more they're all basically gases, although that would actually, this is I think this is urea, so maybe it doesn't matter so much. The physical states aren't clear, but we've got the absolute entropies written up here. Actually, it says gases right here. So they're all gases. What makes the difference is this is a much more complicated looking molecule, and so it's got more ability to be disorderly than these other two smaller molecules. But anyway, so we've got their entropy values. Use the data above to calculate the values of joules per mole per reaction of the standard entropy change. Okay, so what we want to do is add up all the entropy of the products and subtract out all the entropy of the reactants. That's final minus initial to give you the change. Okay, so we have 1 mole of each of those. So we'll add up these two and subtract out that original amount of entropy, and we'll see that there's a net change in entropy. By the way, if you're going from 1 mole of gas to 2 moles of gases, you should expect an increase in entropy. The system is becoming more disorderly because we have more gaseous particles here. Letter B, here's the bond enthalpies. We want to also calculate the enthalpy change. So all of the bonds that we're going to break require energy to break them. All the bonds that we form are going to release energy. So we want to add up all of these, that's the endothermic part, and subtract out all of these, that's the exothermic part. Predict whether the temperature of the contents will increase, decrease, or remain the same. Okay, if this is an exothermic reaction, we don't know yet. We're going to have to do part B first. But if it's exothermic, it's going to release that energy into the surroundings, and the surroundings, the contents, are going to warm up. If it's endothermic, it's going to take some of that thermal energy and get absorbed and store that energy in these chemical bonds here. And the temperature, the thermal energy, is going to drop because it's getting stored as potential energy in here. That's if it's endothermic. If it remains the same, there's only one situation where that would occur, and that's if the change in enthalpy of this reaction is 0. It's very, very unlikely to happen. Chemical reactions tend to be exothermic or endothermic. They're almost never just non-thermic. Okay, experiments carried out to measure the rate of the reaction and its first order. Things to remember about first order reactions are the fact that it's the natural logarithm versus time, which will give you the linear integrated rate law. Also, there is a constant half-life where the half-life is equal to the natural logarithm of 2 divided by the rate constant. Okay, so and that's on your equations sheet. So we can use this information in here to work through finding the rate constant, because that's connected to the natural logarithm integrated rate law. The initial rate, okay, we can also basically solve for the rate at time equals 0. And here, this is not the natural logarithm. This is the reciprocal of concentration. That will not result in a straight line. We know that right off the bat. Okay, that's because this is not a second order reaction. It's a first order reaction based on what they're telling us up here. So let's look at the rubric. Okay, so here's our entropy values. Okay, so we can calculate the change in entropy of reaction by adding up all of the entropies of the products and subtracting out all the entropies of the reactants. Okay, so these two minus this one. Okay, and so we see a positive change in entropy, and that's exactly what I was saying should happen. 1 mole of gas is turning into 2 moles of gas. The system is more disorderly. So now we actually have a number to go with that prediction. Here's all the bond energies. We're going to add up all the bonds that we're breaking, because that takes energy, and we're going to subtract out all the bond energies that form. Okay, so we got to count them all up basically, and so looking at all of the carbon-hydrogen bonds, there's 5 of them here. There's 1 carbon-nitrogen bond and 2 nitrogen-hydrogen bonds, and so they've added up all of those. And the double bond is, we've got to treat that separately. It's its own type of energy. So that's going to get released. 4 of these are going to get released, and then 3 of these are going to get released. Okay, so it's just careful arithmetic basically. So we're trying to add up all of this stuff. Exothermic bonds forming, that's negative. Endothermic bonds breaking, that's positive. Okay? And so final answer is 49 kilojoules per mole. I'm not sure exactly why they've written it 2 different ways here. But, oh, if you think about it, you can kind of simplify what's happening, because there are 4 carbon-hydrogen bonds here, and there's 5 carbon-hydrogen bonds here, and so really there's only 1 of these bonds you have to break or something, technically speaking, and so they're sort of simplifying it down just to have to do less math. But you'll never go wrong if you literally count up everything. But you can just kind of compare and say, well, what's new? What's actually different? And that's what they've done, basically 2 different methods. The net result is right here. It's simpler to calculate. Letter C. Okay, so the value of the rate constant. We've got the integrated rate law for a first order reaction. The rate constant is also hiding in here, so this is how they've gone about solving for it. That's probably the best method because it's not obvious what the half-life is looking at this. You'd have to be very careful if you're going to consider half-life, but you can definitely plug in the values here to solve for K. So the initial concentration, remember, divide by 2 liters, moles divided by liters, so that's the concentration here. And so solving for K, just plugging straight in here. 1 point is earned for the concentration. Okay, that's important because they didn't actually give you concentration. 1 point's earned for the correct set of the first order integrated rate law, and then the correct calculation. So 3 points hiding in that part. Letter E, calculate the initial rate. Okay, well, again, for the initial rate, now that we actually know the integrated rate law, and we know, now that we know the rate constant, and we also know that it's first order, we know the differential rate law. Okay, so just simply by plugging in concentration and rate, the rate constant from this part of the problem, you can solve for that initial rate. This is like plugging in for the method of initial rates. Plug in concentration. With the rate constant, we've got the initial rate. The plot would produce a curve. Had the reaction been second order, it would have been a straight line. And they're basically just clarifying that it's not a second order reaction, it's a first order reaction. Okay, send me a message if you have any questions as you're grading your FRQs. Bye.